All right, guys, hope everybody's doing okay. What we're going to do now is basically pick up where we left off with in our previous lesson, where we looked at the states of matter and we looked at the differences between solids, liquids, and gases. And we're going to actually classify matter in terms of whether it's an element, compound, or a mixture. So we'll kind of compare and contrast all three of those, and we'll look at some different types of mixtures towards the end of this as well. So let's take a look at where we're going to start here, and that is with elements. So what are some examples of elements? Well, you're in chemistry, right? And all of our elements are found in one location. All 118 of them, they're all found on the periodic table. So some examples are silver, oxygen, and carbon, just to name 3 out of the 118 official ones that we have here. So obviously anything on the periodic table is an element, and one of the examples of a compound sometimes students think is an element because it's made up of elements. So some examples of compounds are water, salt, and sugar. And usually it's salt. I'm like, all right, salt an element or a compound or a mixture. And some students will say, oh, it's an element. I'm like, okay, well, where is it? Where is it on the periodic table? And they're like, oh, well, it's made up of sodium and chlorine. I'm like, okay, so it's made up of 2 elements. So it's not an element. Okay, it's 2 of them combined chemically. So it's a compound. So water, salt, sugar are all compounds. All compounds have an exact chemical formula. So you may know that the formula for water is H2O, salt is NaCl, and there are various types of sugars. And one of the formulas pops up here a little bit later, I think, for that. But glucose, fructose, sucrose, so like they all have different formulas that are similar, but just differing in number of carbons, and therefore hydrogens as well. So and oxygen. Let's take a look at mixtures. Most things are mixtures. Okay, a lot of things are mixtures. So examples I have might make you hungry. Chex Mix, chili, and Kool-Aid. All right, so I have 2 mixtures here that are basically solid components, and then Kool-Aid is, before it's actually a solution, it's a solid and a liquid, and you have some dissolving going on there, but you can see that these are examples of mixtures. Let's go back to elements and classify those as heterogeneous or homogeneous. So elements are homogeneous, and what does that mean? You might want to add this to your note sheet. Homogeneous means consistent throughout, okay? Heterogeneous means inconsistent or not the same throughout. So if you took a hunk of carbon, and a good example of that is like a piece of charcoal, took a hunk of carbon and cut it in half, slice it in half, it would look consistent all the way through, okay? Same thing with a bar of silver, or like a hunk of silver, okay? Or oxygen gas, okay? All the oxygen gas is like it's the same throughout, okay? So that's what homogeneous means. All elements are homogeneous. Same thing with compounds, okay? They're all homogeneous as well. So if you have a glass of water, that glass of water is the same throughout. It's consistent throughout. Same with like a block of salt or sugar, right? It's the same throughout. It's consistent throughout. Mixtures, though, are not, okay? So chili might not be the same throughout. Okay, so you might have some components of it that are more on one side than the other side, or Chex Mix. Not every bag of Chex Mix is the same, right? You have the best kind, which is clearly the cheddar Chex Mix. I don't know if you agree or not with me on that one. And there are some parts of that that might be on one part of the bag versus the other. It's definitely not the exact same consistency throughout that. So mixtures are going to be heterogeneous, with the exception of a certain type of mixture, which can be homogeneous. So homogeneous mixtures are actually called solutions. And the example up here that's a solution is Kool-Aid. So you might have been thinking as I was going through that, Kool-Aid is, like once you make the Kool-Aid, okay, and it's fully mixed, and your solution's made, it's all the same throughout, right? It looks the same throughout. It's the sugar is evenly dispersed throughout. So solutions are homogeneous, okay? So elements are homogeneous, mixtures are homogeneous, or compounds are homogeneous. Mixtures can be heterogeneous or homogeneous depending on the type, okay? So that's something to just keep in mind here when we're looking at these. So let's go back to the elements and define as pure or impure. You may think, if you were to take a guess on this, you'd say elements are definitely going to be pure substances, and you'd be correct. So what is a pure substance? Something else you can add to your note sheet or think about here. A pure substance is a substance that has a definite set physical and chemical properties. So you could look a lot of these up. Like oxygen has a density, right? Silver has a density, carbon has a density, and it's the same no matter how big or small your sample of these elements is going to be, right? Carbon has a melting point. Carbon has a boiling point. You could look those up. It's the same at standard conditions. And that's going to be the same for compounds as well. Okay, so they are going to be pure substances as well. Water has a freezing point or melting point, right? It's 0 degrees Celsius. Water has a boiling point. It's 100 degrees Celsius. And if you're at standard conditions, that doesn't change. All right. Water has a density. It's 1 gram per milliliter. Salt and sugar, same thing. But once you get to mixtures, not necessarily true for that. So mixtures are going to be impure. Okay, all of them are. Whether they're homogeneous or heterogeneous mixtures, they're all going to be impure substances. There's no definite set of chemical properties for chili. There's a million different recipes for chili, right? There's different flavors of Kool-Aid. Chex Mix, there's the best kind, which is the cheddar kind, and there's all sorts of other flavors of Chex Mix. There's no definite set of chemical properties or physical properties for Chex Mix. Okay, it doesn't have an exact chemical formula, so it doesn't have a definite set of properties you could look up. Okay, so elements and compounds, you could look those up, online. You can look them up in a textbook or a reference book of chemical elements and compounds, and you could look up those definite values. Not the case for mixtures. All right, going back to elements, these are composed of things called atoms. Okay, so what is an atom? Let's define that. An atom is the smallest piece of an element that still retains the properties of that element. So what's that mean? If you took a piece of silver, okay, you had a big hunk of silver, and you cut that in half, you'd still have 2 hunks of silver, but they'd be smaller, right? Take one of those hunks, cut that in half, cut that in half, and keep taking the smaller piece and cutting it in half. Eventually, you're going to get down to what? Like, 2 atoms of silver, right? And then you cut that in half, and you're going to have 1 atom of silver. If you try to cut that in half, hypothetically here, if you were to cut that in half, you're not going to have silver anymore. You're going to have 2 other elements that are actually being created, okay? So if you take that larger piece you have and keep cutting it in half and go as small as you possibly can, you're going to be left with 1 atom of silver. That 1 atom of silver has the same exact chemical and physical properties as the big hunk of silver that you started with. Okay? So that's the smallest piece of an element that still retains the properties of that element. It's the same color, same density, same texture, all that stuff. You know what I mean? So that's what we want to look at here. So these are the atoms. They're on the periodic table. There are elements, right? Wrong slide there. Okay? So that defines that for us. If you go to compounds, it's similar. I just got all messed up here. Compounds are made up of 1 type of molecule. Okay? Let's define that, and then we'll come back here. Okay, so what's a molecule? You're going to say, this is really close to the last definition we looked at, and you're going to be right, but there's a minor difference here. So a molecule is the smallest part of a compound, since we're talking about compounds now. Smallest part of a compound that still retains the properties of that compound. So all I did here was take out the word element and replace it with compound. It's important though, because if you think of water, you have a glass of water, dump half of it out. You still have half a glass of water. Dump half it out. You still have half of that amount left. Keep getting rid of half of what you have. And you'll eventually have 2 molecules of water. Okay? And then, okay, dump half of it out. You're left with 1 molecule of water. It's not an element because it's made up of multiple atoms, right? You have 1 molecule of H2O left. Okay? That 1 molecule of H2O has the same properties as the glass that you started with. So it has 100 degrees Celsius for the boiling point, 0 degrees Celsius for the freezing point, 1 gram per milliliter for the density. That 1 molecule has that. As soon as you split that molecule up, you don't have water anymore. You don't have a compound anymore. You have the atoms that have made up the molecule. Okay? So here's the definition of a molecule then. It's made of 2 or more atoms that are bonded chemically. And you're going to say, isn't that the same as the definition of a compound? Okay, the compound is two or more different atoms bonded chemically. All right, so if you have H2O, that's hydrogen and oxygen. Those are your two different atoms, okay, bonded chemically to make up water. A molecule is just simply two or more atoms bonded chemically. All right, this is where it gets a little bit kind of tricky here. And if I were in person, I would have different models to like physically show you to make it a little bit easier to understand, but I'll do my best here. Elements and compounds can be made of molecules. All right. Some elements, see if I could draw on here. Some elements are diatomic. Okay, so let's take a look at what I mean here. Hydrogen is a good example. Well, actually, let's just do oxygen, because that was on the element slide. Oxygen exists in nature as O2. There's an oxygen bonded to another oxygen. Okay, that is one oxygen molecule here. Okay, how do you classify that though? Well, it's still an element. Okay, it can't be a compound, right? Because they're the same atom, they're the same element being bonded together. Whereas if you have water, you have H2O, right? So here's your oxygen, and then you have your two hydrogens bonded to it. Pretend that's shaded in there, okay? So that's water. Oops. That's H2O. Two H's and one O, okay? So this is a molecule because it's two or more atoms bonded chemically. Fine. This is oxygen, right? This is also a molecule because it's two or more atoms bonded chemically. But let's go a little bit further. They're both molecules. But here, with two oxygens, that's a molecular compound, or I'm sorry, molecular element. There we go. All right. Molecular element because they're all the same. Okay? And over here, water is a molecular compound because they are two or more different atoms bonded chemically. All right? So that's important. Let me erase this on here so you can see what I have. If a sample has molecules made up of only one type of atom, it's an element. Already went over that. That was the drawing here on the left. And some elements are diatomic, like I just went over with oxygen there. So oxygen is diatomic, okay? It only exists naturally as O2. Hydrogen is another example. It exists as H2. There are actually 7 diatomic elements on the periodic table. Those are some on the slide here. You have H2, you have N2, you have O2. You also have F2, Cl2, Br2, and I2. All right? So fluorine, chlorine, bromine, iodine, nitrogen, oxygen, and hydrogen. We'll add those to our periodic table a little bit later. But if you want to know what all of them were, that is what they are. Okay? If a sample has molecules made up of one or more than one type of atom, that's a compound. Water, CH4 is methane. That's what's in that's the gas we use in school to light the Bunsen burners. All right? So that is a lot of information there on this one slide, but it's really, really important foundational information that we need to know. Okay? So let's go back to where we were here. Go back to compounds. So there are two or more types of atoms chemically bonded and made up of one type of molecule. So that's important. 2 components there of our compound definition. If we go to mixtures, and go back to where we were, mixtures are impure, as we said, and they are physically bonded. So it's 2 or more types of atoms or molecules physically blended. Okay, so another example of a mixture is salt water. Okay, so you have water, which is one compound, salt, which is another compound, and they're physically blended. That dissolving process is actually a physical process. Okay, so most things are mixtures, like I said. They don't have a definite chemical formula. You can make salt water with 1 grain of salt and a bunch of water, or a cup of salt and a bunch of water. You know what I mean? So there's no definite formula for those. Okay, 2 or more types of atoms or molecules physically blended. There's no chemical bond between them. There's no chemical bond between the Kool-Aid particles and the water molecules. You know what I mean? So it has to be a mixture. There are some activities and different things we could look at to if we're in class to help us understand these a little bit more. Okay. All right, elements, they cannot be separated, period. Okay, you're going to say, well, yeah, you can split atoms. Correct, you can. But then it's not the same element anymore, right? We talked about that. So you can split silver, right? But then it's not silver anymore. You can split uranium. That's not uranium anymore. So for what we're saying right now, that's all nuclear chemistry. For what we're saying right now, generally speaking, elements cannot be broken down and still be the same element, retain the same properties. Compounds can be, and it's really interesting, they can be separated chemically. We'll get to that. Not physically. All right, physically is like with dissolving or boiling or evaporation, like physical separation yourself. Chemically means through the form of electrolysis, which we'll get to when we talk about methods of separation, which is a different part of this unit. All right. Mixtures can be separated physically. All right. So elements cannot be separated, period. Compounds can be separated chemically. Mixtures can be separated physically. So how do you separate Chex Mix? Well, you pick out all the good pieces first, and then you eat the Chex Mix pieces, or those little like cracker pieces, right? You put those off to the side. Eat the more like bland stuff first, right? Like the pretzels, and then you go back and eat all the good stuff, right? So you can separate that physically. If you want to separate Kool-Aid, you could actually take your Kool-Aid mixture, heat it up on the stove. All the water will evaporate, and what will you be left with? You'll be left with the Kool-Aid, like the mix, okay? It'll be in like a sugary, slushy form, but it'll still be the Kool-Aid mix and not the water, because it'll be evaporated and gone. Okay, so that's an example of a physical separation. There are way more examples of physical separation, but we'll save those for a later point in time. Okay, elements are the simplest form of matter, and here's a picture of those. So we'll do some practice with this where we look at different images and determine if it's an element, compound, or a mixture. But you can see these dots in here, those are atoms, and they're the certain coloring represents like what type. These are a bunch of atoms. They're all of the same variety, so it's an element, so we classify that. Compounds. This is super neat. I love this. I think it's so interesting. Each substance gains a new identity with a compound. The perfect example here is sodium chloride. Okay, so let's take a look at that actually, and you'll see what I mean. This is super interesting. See if this works. So we have sodium as one example. Okay, so sodium chloride, NaCl, salt, is made up of two elements, right? So we have Na, which is sodium. What do we know about that? Anybody know anything about sodium? If you do know anything about it, it is extremely reactive. It's like a really soft, silvery type of metal, and it is extremely reactive with water. Okay, like really, really dangerous. Let's watch a little clip here on that, and then we'll move on to our other type. Okay, or our other component of salt.
Sodium. Symbol Na. 11 protons and 11 electrons, arranged in shells as 2, 8, and 1. Sodium is an alkali metal. Like all the elements in this group, it's desperate to get rid of that extra electron.
You cut it quickly.
I should see some
You should see a silvery surface inside.
Indeed, wow!
It slices like cheese, but it's actually a soft metal. Teo's offered to put on one of his favorite sodium demonstrations. What happens when the pure element dumps its outer electron in a violent altercation with ordinary water?
Nice.
Boom!
What we're seeing is what happens when sodium's extra electron tears apart water molecules, releasing flammable hydrogen gas, the H in H2O, which explodes when it mixes with air.
Okay, so now we're going to add chlorine to the mix. All right. If you know anything about chlorine, you know it's like a yellowish, green, poisonous gas. Okay. Short video clip on chlorine. Let's see what happens there.
Is chlorine. 17 protons surrounded by 17 electrons, arranged in 3 shells of 2, 8, and 7, one short of being full. It's that extra electron chlorine will get any way it can. sometimes with violent results. That's why chlorine gas was used as a deadly poison in World War I.
Okay, now the best part about all this, super neat. You can take sodium, which blows up when it hits water, right? Super dangerous. You can take chlorine, which you breathe it in and it's going to kill you, right? Poisonous gas. You take two like horrible, dangerous things, put them together, right? Like, this is so interesting. And what do you make? You make salt. Okay, you put it on your popcorn, right? Or your French fries. Why? How does that happen? Let's watch this little clip here and we'll take it from there.
The next day, Teo takes it up a notch. As if sodium plus water weren't violent enough, now he wants to combine the same deadly sodium with another lethal element, chlorine, one of the halogens. The result, he claims, will be a tasty flavoring for a net full of popcorn?
Isn't chlorine deadly poison?
Absolutely. I mean, chlorine, they used it as a poison gas in World War I.
It'll be perfectly safe when these two deadly ingredients combine.
I didn't say that. I said that after they're combined, the result is perfectly safe. The actual process of combining them is fraught with difficulties.
Okay, and that's why we're dressed up like miners here.
First, a hunk of sodium in a dry metal bowl. Then, a jet of pure chlorine. Surprisingly, no explosion. Somehow, when these two bad boys of the periodic table come together, they calm down. At the atomic level, sodium, an alkali metal, had an electron it didn't want, and chlorine, a halogen, wants desperately to grab an electron. Once the handoff was complete, both atoms wound up with full shells, making them stable, and able to join together to form a crystal compound we can't live without. Sodium chloride, table salt.
Now, I don't exactly see, like, a pile of salt anywhere.
Now, the salt, most of it went up in the smoke. It went in the popcorn.
Tastes like salt. The good stuff. Fresh.
Fresh
Even
salt.
the freshest salt at Teo's farm.
Okay, so if we go back to compounds here, each substance gained a new identity when it created, like the Na and the Cl came together to create salt. Like, amazing, right? How do you take two things that, like, on their own could kind of kill you, then you suddenly make something that is, like, so common and safe, and you put it on your food, right, to make it taste better. That's one of the things I really love about chemistry and how that works and why that works. I think that's really interesting. So, moving on to mixtures here, along the same lines. Do new properties form from mixtures? The answer there is no. Each substance retains or maintains its identity. So the Chex Mix, you still have like the different pieces having their different individual flavors and textures and all that. It's not like you put them together in the Chex Mix bag and they all taste the same, and all look the same and everything. You know what I mean? Or they'll look different. You know what I mean? They are all the same, is what I'm saying when you have them in the bag. It's not like the pretzels taste differently and turn into something else like it would with a compound. Whatever it looked like before, and like the properties, I should say, it had before, it will have those again. It will retain those, maintain those once the mixture is created. Okay? So, compounds, the components gain new identities and properties once created. In their compound and mixtures, they maintain the same identity. Okay, we basically finished elements, so let's go to compounds here. The ratio doesn't matter. The answer there is yes. Here are your formulas up here. So water is H2O. It has to be H2O to be water. If you have H2O2, you don't have water anymore. You have hydrogen peroxide. Not going to want to really drink that, right? So you have your formula, your ratio, that does matter. Salt is always NaCl. It's not NaCl2, right? It's always NaCl. As soon as you change that ratio, you change the compound. Mixtures, though, there's no definite ratio. Like, you might get a bag of Chex Mix that has more of one piece than the other. The next bag might have a different amount. You know what I mean? There's no definite ratio there, and it's really not important. You can make Kool-Aid with 1 scoop of Kool-Aid mix and a bunch of water, or if you're into Kool-Aid and you need that to be really strong, you put 5 scoops in, right, or whatever it is. It's still Kool-Aid, right? But the ratio isn't like a definite ratio, right? You don't have the same exact ratio of Kool-Aid every single time you make it. So let's look at the visual for compounds. Looks like this. So you can see that you have two or more different atoms. You have the black and white, and they are chemically combined. So how many molecules are in this picture? Because that's what we are creating here, right? So we have a molecule right here, right? 6 of them, obviously. And within this molecule, you have 4 black atoms and 2 white atoms, whatever they represent, whatever elements they are. Same thing with these. Every single molecule here is the same, all right? So some students are like, oh, we have a mixture here. No, you don't. Okay, there's no mixture here at all. You have a compound because every molecule is the same. Look right here, made of only one type of molecule. Okay, so you have 6 of the same molecule, so therefore you have a compound because they are 2 different atoms combined. Just to, what am I doing here? Just to be complete here on this. If I had another example, here's another box. Oops, I'm a mess. Okay, so if I did this, if I had that, okay, I had that. Let's add another one for fun. Okay, I have these, they're all the same element here. There's these white, whatever it is, white elements, okay? How many molecules are in this picture that I just drew? Well, there's 3, okay? I have 3 molecules here. So do I have a compound? Well, no, because every single atom here, like in this molecule right here, okay, both atoms are the same. So what do I classify that as? This is an element, okay? All 3 molecules are the same, and every molecule is the same element. It's made up of the same elements, okay? So I have 3 molecules here, all identical, all of the same element, okay? So here's an element, another example of an element. Here's a compound. Let's look at how mixtures are, okay? And then we'll go from there. Now, mixtures, you can see that you have a bunch of molecules here. How many molecules are there? Well, you have, let's count them up. You have 1, 2, 3, 4, 5, 6, 7, 8. 8 molecules here. Are they all the same, though? The answer to that question is no. I have one type of molecule here. That's a compound, right? And I have this molecule here. That's what I was trying to draw on the last slide. And this is an element. So what do I have? I have a mixture in this box. I have a mixture of elements and compounds. Okay? So you see there's no bond between them. There's no bond here, right? So it's just a mixture of elements and compounds. Okay? No chemical combination between the two there. Okay? That takes care of the difference, comparing and contrasting all three types here. So you can take a look at this, and you can actually pause the video and try this. All right? You can see that there are, like for number 1, it says pure elements. There are 3 of them here. Okay? So you have A through H. 3 of those are pure elements. 2 of them are elements made up of single atoms. All right? And then you can go through the rest. So pause the video, give these a try. We'll go over them real quick and see how we did. So number 1, you have pure elements. There's 3 of them. Well, A is a pure element. Okay? So we have A. What else? C and D. Those are all pure elements. 1 type of atom. That's it. Number 2, elements made up of single atoms. Okay? So out of A, C, and D, 2 of those, because they're atoms, right? They're elements. 2 of those are elements made of single atoms. Well, that is going to be A and D. Number 3, elements made up of molecules. Well, that would only be C. Okay, so that's our element here. And you have 3 molecules. Okay, they're all the same. All right, mixtures. There are 4 of them. So B is definitely a mixture. Let's see. E is a mixture. F and H. Those are all mixtures. Number 5, pure compound. Well, it can't be A, C, or D. Can't be B, E, F, or H. So we're left with G. That one. Okay. You have one type of molecule here, and that molecule is a compound. Right? This looks like water here. A mixture of two compounds. There's only one of those. So my mixtures were B, E, F, and H. One of those is a mixture of two compounds. That would be B. And a mixture of two elements. There are two of those. E is a mixture of two elements, both in the atom form, and F. In F, one of them is an atom, and one of them is a molecule, but they are both elements. Okay. So hopefully we did okay with that and kind of understand that as we go forward here. All right, so let's wrap this up here by looking at different types of mixtures. Okay, so again, we have heterogeneous versus homogeneous. You can see that heterogeneous is different throughout, not consistent throughout. Homogeneous is consistent or the same throughout. And you'll see this on milk. You can see right here, it's homogenized. Okay, so part of milk is the fat, right? And you don't have a big fat blob sitting on top of the milk. Basically, the homogenization process is when they take the milk or the fat, they like pass it through a really fine like screen, simplifying this, and it turns it into like from one big blob of fat into a bunch of like fat, like tiny fat globs, right, that float around in there. Okay, so that's the homogenization process that we're talking about here. So you have 2% milk fat, 1% skim milk, which is hardly any, if any, fat at all. But that's what that means if you see that on there. So a little real life application here. So one example of a mixture that is a solution. We talked about that already a few minutes ago. A true homogeneous mixture. So solutions are homogeneous. All particles are broken down into individual molecules or ions. So that is really important here. Let's take a look at a little animation for that. Okay, so here we go. I have water, and I'm going to start the animation here. We're going to add something to it, and it will zoom in for us. Let's start it and check it out. Looks like I dropped a cube of some sort, a sugar cube in. And now we're going to look at the dissolving process. So let's see, I can't pause this, so we're going to try to narrate through it. Here's one example of sugar, C12H22O11. See the water molecules coming around and attaching itself to those and pulling the individual molecules away. So you have a big clump of sugar, and then when you stir it around and it like dissolves, you end up with a bunch of individual sugar molecules, individualized ones, right? All get carried away. And then if you look at it, then you don't have that big clump of sugar anymore. When it zooms back out, you have sugar water. Okay, so you can see that all those are still in there, but they're separate now. They're all floating around. And they're doing an electrical conductivity test here. Sugar does not conduct electricity very well, which we will talk about in a later, at a later point in time. Since the molecules and ions that the substance breaks apart into are so small, a beam of light will pass straight through it with no dispersion. So here's a beam of light, like a laser pointer if I was in class. I would shine it at a true solution of like sugar water or salt water, and the beam would pass right through. You wouldn't like see the beam within the solution at all. Okay, no beam, the light beam is not visible. I have an example of when it is a little bit later. Two parts of a solution. You have a solute and solvent. So the solute is what is being dissolved, and the solvent, with the V there, does the dissolving. Okay. Water is called the universal solvent because it is polar. Probably learned about that in bio. In fact, I know you did. Water is polar, and it dissolves many, many things. That's why it's called the universal solvent, because it does such a good job at dissolving things. Not everything, like oil, right? But that's a discussion for another day. But it does dissolve a lot of things, so it's called the universal solvent. So some examples of solutions are soda, iced tea, lemonade, salt water, sugar water, Kool-Aid we already mentioned. Soda not only has a bunch of sugar dissolved in it, that's obviously not too good for you, it also has a gas dissolved in it, which is carbon dioxide. That gives it the carbonation. So you can have some solid being dissolved. You could also have a gas being dissolved, which is what soda has. It has two things dissolved in it, not just the sugar that everybody thinks about. Okay, colloids. These are really interesting because they look homogeneous, they appear homogeneous, but they are truly heterogeneous. So let's take a look at that. They break down into small clumps of molecules, not individual molecules. Okay, so the clumps, don't need to worry about the size here, but they're between 5 and 200 nanometers. Too small to be seen with the eye. Like you can't really see, milk is an example of this. You can't really see those clumps of milk fat in the milk, right? Since milk is an example of a colloid here. Colloids get a little more interesting and in-depth. You could have solids within solids, liquids within solids. It gets a little bit more confusing. But fog is a common example. Butter, mayonnaise. I say milk, like I already said, milk's an example here. They're like, look kind of cloudy. Okay, because those globs of, those clumps of molecules that they have in them. So you can do a Tyndall effect test on something to see if it's a colloid or not. And a Tyndall effect means the light is going to scatter as it passes through it. So think of like if you have like the sun like shining through a window in your house. It's a really bright day, and you think your house is really clean, and then you look at that light coming through, and you're like, oh my goodness, I see all the dust in the air. That's a perfect example of the Tyndall effect, like a colloid being created like in your house. Another example is if you're driving and it's foggy and you have your lights on, obviously, like if it's nighttime, it's harder to see because the light is shining off of all that fog, the water molecules in the air. That's a colloid as well. And that's the Tyndall effect test. That's the Tyndall effect in action right there. That's a real life example. If you've ever seen The Big Bang Theory, there's a clip where they play like laser chess or something like that. And they try to get from one end of the room to the other with this laser system set up. And you can't see the laser system until they spray like a hairspray or like compressed air into the room. So the light bounces off of it. Okay. Think of if you go to a concert or like there's like any sort of laser show component. What do you always see when there's a laser show? Well, you always have to have smoke or some smoke machine, right? The smoke machine is so that the light can bounce off of those particles and you can see the lasers. If there's no smoke or smoke machine with your laser show, it'd be the worst laser show ever because you wouldn't see anything. All right. So that's how that operates. It's a Tyndall effect. You can watch the clip down here if you want to see that part of this TV show. Here's what it looks like when you're passing it through a colloid. All right, you can actually see the beam bouncing off of the tiny particles in there. Okay, the tiny clumps of a colloid. So you have two liquids here. They both look the same, but clearly they're not. So you can do the Tyndall effect test to see if you have a solution or a colloid. So you can see your solution over here. Light beam passes through, really passes through both, but you can't see it in the solution. Particles are too small for the beam to bounce off of them. And then here with your colloid, the particles are a little bit bigger. The light bounces off of those here, okay, and you can actually see it. So left solution, right colloid. Finally, suspensions, to wrap it all up here. Suspensions have the biggest particle size of the three. So solutions have a very small particle size. Individual atoms or ions are molecules. Colloids are clumps of molecules. And then suspensions, they are particles that are big enough to be separated by a filter. Large particles fall to the bottom. You want to think about like Italian salad dressing. You need to shake that before you put it on your salad, right? Paint, you need to shake up that can of paint because all the particles sink to the bottom. Antibiotics is another one. You should shake those up. I know that because my kids have had more than their fair share of ear infections, which involved antibiotics all the time. So I always have to shake those up before you get the medicine so they get some of the actual medicine when they take that. But those are examples of suspensions where the particles are big enough to sink to the bottom. Okay, that takes care of a lot of stuff, honestly. Elements, compounds, mixtures, and types of mixtures. So the next thing we're going to look at is really, really neat. It's chemical versus physical changes. You already saw a little bit of that with the salt examples. With the sodium chloride that we made in the video clips here throughout this lesson. And then we'll take it from there. All right, guys. Thanks a lot.